Section 6.2 is on inverse functions and relations. An inverse relation is the set of ordered pairs obtained by exchanging the coordinates of each ordered pair. So a relation is just a set of ordered pairs. To get the inverse of that relation, you just switch the x and y in each ordered pair. An inverse function is an inverse relation that is a function. In other words, it meets all the criteria of being a function, not just a random set of ordered pairs. We write it with this notation. Looks like f negative 1x, but it's not f to the negative 1 times x. We say that that is the inverse of f of x. This negative 1, if you remember that from like the inverse sine and cosine, is just a notation that means the inverse. So f negative 1 of x is read as the inverse of f of x. So our first example here says to find the inverse of this relation. 6, 7, negative 3, 0, and 4, negative 8. Very simply, just write it in set notation, switch the x and the y. So instead of 6, 7, I have 7, 6. Instead of negative 3, 0, I have 0, negative 3. And instead of 4, negative 8, I have negative 8, 4. Make sure you do your curly brackets, your commas between the ordered pairs. That's your answer. Okay, now let's find the inverse of each function and then graph the function and its inverse. So f of x is x minus 4 all divided by 3. That can also be written as 1/3 x minus 4/3, because that 3 on the bottom applies to both the x, and there is like an invisible 1 there, and it also applies to the negative 4. And notice that that's going to be the same as y equals 1/3 x minus 4/3, so we can use slope-intercept form to graph it. Now, to find its inverse, the first thing I want to do is I'll take the original function and write it with a y instead of f of x, because remember, f of x is just really a fancy way of saying y. Second step now is to switch the x and the y. So instead of y, I'll have an x, and instead of x, I'll have a y. Okay, so x equals y minus 4 over 3, but it's hard to graph it in that form, so let's put it into slope-intercept form. Let's multiply both sides by 3, and then let's add 4 to both sides. And then let's flip-flop it around so it looks like it's in y equals mx plus b form. Okay? Oh, and then the last step is to put back in the inverse notation. So the inverse of f of x equals 3x plus 4. So the inverse of f of x equals x minus 4 over 3 is the inverse of f of x equals 3x plus 4. Now I need to graph each one of those. I'm going to do this one in pink. I'll do this one in purple. And actually, I think I'm going to start with the purple one because that's a little easier. So it's in slope-intercept form, so I'm going to begin with my b. And then I'll go up 3 and right 1. Down 3 and left 1. And that is the inverse of f of x, so I'll draw that. Make sure I counted right. Okay, I'll go ahead and label that. Now, to do this one here, that's going to be kind of a pain because my y-intercept is negative 4/3, which is negative 1 1/3. So I think I'm going to graph this one and see what it looks like. So let's graph it. So I'm just going to leave it in that form, parentheses x minus 4, close parentheses, divided by 3. Let's see what it looks like there. Okay, yeah, in fact you can see right here that you've got your y-intercept as a fraction. So I'm going to go to my table and I'm going to look for a few nice points that I can graph. So actually it looks like negative 5 is a good point. So negative 5, negative 3. Looks like negative 2, negative 2. And 1, negative 1. Let's see. So let's go ahead and put those on a table over here. Oops. Let's make a little XY table for us. So I had -5, -3, -2, -2, 1, gave me -1. And notice what's happening here is my y's are going up by 1 as my x goes up by 3. So let me try 4 and 7 also in my table. What if I put in a 4? I get 0, that's good. And a 7, that gives me 1. Okay, great. So let's go back over here and we'll put in 4, which gave me 0, and 7, which gave me a 1. That should give me enough points. So -5, 2, 3, 4, 5, -3, -2, -2. Oh, look at that, they cross each other. 1, -1. And actually from here I could continue just with my slope. Notice it's up 1 and right 3. So up 1 and right 3, up 1, right 3, 1, right 3. And that is my original f of x. So the inverse of the original function is 3x plus 4. The graph of that is in purple. The original function is graphed here. Now one thing I want you to notice, and this is always going to be true of all inverses, is that they are actually reflections over the line y equals x. So the line y equals x, okay, whatever x is, y is the same thing. So that's 1, 1, 2, 2, 3, 3, and so on. I'm going to graph that line right here. And that's the line y equals x. Notice that the pink line, if you reflect it, kind of flip it over the green line, it becomes the purple line. So inverses are reflected about the line y equals x. Note the reflection about the line y equals x, and that's going to be true of all inverses. Let's take a look at another example. This one involves a quadratic. Here we have g of x equals x squared plus 4. So let's go ahead and find its inverse. So let's write it as y equals x squared plus 4. Switch your x and your y. So x equals y squared plus 4. Solve that for y. I'll subtract 4 on each side. And then I'm going to take the square root of both sides because I need y all by itself. To undo a square, I need to do the square root. So y is going to equal the square root of x minus 4. And whenever I do that, I have to do the positive or negative square root. So y equals plus or minus the square root of x minus 4. And to clean that up, we're going to use function notation. So the inverse of g of x is the positive or negative square root of x minus 4. Okay, so there's my inverse. Now I need to graph these. And again, I'm going to do them in different colors so that it's kind of obvious. And these are maybe a little more difficult, so I think I'm going to go to my calculator and take a look at it. So, and actually I can graph both of these at the same time on here. So let's do x squared plus 4. And I don't have a positive or negative button here, so I'm going to have to do this next one in 2 parts. So I'll have to do the square root of x minus 4 and the negative square root of x minus 4. It's actually going to graph that in 2 pieces, but they'll both be the same. And you know what, for fun, I'm going to put in the line y equals x so that we can actually see what the reflection looks like. Okay, so let's graph. There's y equals x squared plus 4. There's the positive square root of x minus 4 in red, and then underneath it, the negative square root of x minus 4, and there's my line y equals x. It doesn't look like it's an exact reflection, and that's because my screen is longer than it is high, and this goes from -10 to 10, as does this. So my spacing between the dashes is not the same. To change that, if I go to zoom and go down to 5, zoom square, it'll actually make my screen square, so that now when it graphs the two functions, actually the second one is not a function, technically, because it doesn't pass the vertical line test, and it graphs the line y equals x, it will look more like a reflection. Okay, so let's get some values here. Let's go to the table, and I'm going to try -2 through 2. Okay, and notice that's really good for my y sub 1, which right here was the x squared plus 4. So maybe I'll copy that table over here. I'm going to do that. So for my pink one, maybe I'll just do it in pink. And so that gave me -2, 8, -1, 5, 0, 4, 1, 5, 2, 8. And now I'm going to need one for, actually, you know what, I'm going to change that. Hold on, let's not make that y. Let's be official here and make that g of x. Okay, and now I want to make a table for the inverse of g of x, and I was having a little bit of problem with the table back there on the calculator. So let's take a look at that. Yeah, notice all of these, remember I had to do it in 2 parts. I used both y sub 2 and y sub 3, and I have a whole bunch of errors. That's because, notice in the graph here, I'll go to the graph so it's a little bit bigger. Notice this function doesn't start until x equals 4. So let's go to the table, and let's try 4, 5, 6, 7, 8. Okay, so those are those are nicer numbers, except I have some decimals in there. So when x is 4, both of my y's are 0. Notice that when x is 5, I have a positive and a -1. And I'm going to use x is 8, I have a positive and -2. So let's go ahead and put that in our chart. So I had 4, I had 0. When x was 5, it was both a positive and a -1. And when x was 8, it was both a positive and a -2. So let's go ahead and graph those. 4, 0, 5, positive 1, 5, -1, 8, positive 2, and -2. Okay, so that's g, the inverse of g of x. And then here I had 0, 4, and there we go. And that was g of x. And then for fun, let's just go ahead and graph my line of reflection, which is the line y equals x, and you can see real clearly that it is indeed a reflection about that line. Okay, now you can tell if two functions are inverses of each other if both of their compositions are the identity function. In other words, f of x and g of x are inverses of each other if f of g of x is equal to x and g of f of x is equal to x. So we're going to use composition of functions, just like we did in the last section, and if both of the compositions are equal to x, then the functions are inverses of each other. So let's take a look at a couple examples here. So determine whether each pair of functions are inverses. So what I need to do is find f of g of x and then find g of f of x. And if each of those is equal to x, then they are inverses. If they're equal to something else, then they're not. So recall what this is I start with f of x and I put g into it. I'm going to go ahead and write it out like this, just because that makes so much more sense to me. So start with f, 3, and then I'm going to put in g into there for x, 1/3 x plus 4, and then I have the minus 3. So that's 3x minus 3, putting in g of x for x. Let's clean that up a little bit. Distributing, I have x plus 12 minus 3, which is equal to x plus 9. Oh, that is not equal to x. That has to equal x, so no, these are not going to be inverses of each other. Just to check, I'm going to go ahead and do the second one. It's good practice. So I need g of f of x. So starting with g, which is 1/3, times x plus 4. Did I do that right? 1/3 x plus 4, 1/3 x plus 4. Okay. Distribute x minus 1 plus 4, which is equal to x plus 3, which is not equal to x, so no, that does not equal x. Actually, they both have to equal x, so no, these are not inverses of each other. Let's take a look at our last example here. Excuse me. F of x is 2x squared minus 1, and g of x is the square root of x plus 1 over 2. Let's start with f of g of x. And this is going to get a little sloppy. That's okay, we can do this. So 2 times x, and remember this whole thing here goes in for x, square root of x plus 1 over 2 squared minus 1. So this is basically 2x squared minus 1. Looks nasty, but it's really not that bad. So the 2 is going to be multiplied by this squared. So the square root squared is just the stuff under the square root sign. So x plus 1 over 2. This squared and the square root cancel each other out. That's going to give me, now 2 times that, my 2's will cancel. X plus 1, those 2's cancel each other out, so I have x plus 1, and then minus 1, that's equal to x. That's a good thing. So f of g of x equals x. Now let's see if g of f of x is also equal to x, because both of those have to be true. So I'm going to take g, and I'm going to put f into it. Oh, that looks a little messy too. That's okay. Square root x plus 1, and my x is going to be 2x squared minus 1. That's my x plus 1 all over 2. I'm going to go sideways here. So that's going to give me the square root of, well, I don't really need the parentheses here, so those cancel each other out. So I have 2x squared minus 1 plus 1, which is 2x squared over 2. My 2's cancel each other out, so I'm going to end up with the square root of x squared, which is just x. So here I had an x, here I have an x. So yes, these are going to be inverses of each other. Okay, since g of f of g of x is equal to x and g of f of x is equal to x, they are inverses of each other.